Thank you for coming today on this last snowstorm of winter/spring. We hope. So I wanted to talk today about my work in air quality engineering, and specifically how we can use our understanding of the health effects of air pollution in air quality management. Really important point before I begin on the acknowledgements. So I'm lucky enough to be up here and talk about this research that I and several other people worked on. Faculty collaborators like Jason Hill, Dylan Millay, and Jill Baumgartner, who I met through Institute of the Environment. The graduate students and researchers who did all the heavy lifting involved in this work, and the funders, outside funders and internal to the University of Minnesota, including IonE. So thank you to them. Now, if you're like me, when you saw the title of my talk, you might have responded with something like this, like, really, air pollution kills? Is that right? I'm in this business of air pollution research, and every day I'm surprised at how large are the health effects of air pollution. So what I wanted to do today is, the first half of my talk is on what are the health effects of air pollution, and how do we know what they are. And then in the second half, I'll give you 3 examples of research projects that I'm involved in. So the story of air pollution often starts here with London in 1952. Now, of course, air pollution is not new. It goes back hundreds or thousands of years to the first cavemen building a fire inside a cave and being exposed to indoor air pollution. In the case of London, there were large amounts of air pollution there for hundreds of years, and there were efforts in the Middle Ages to try to address air pollution unsuccessfully. And then it comes up here to 1952, when there was a really high pollution episode. The air was stagnant over London, and the pollution just built up and built up from cars and factories, from coal, which was used for heating, home heating at the time. There are all kinds of wonderful stories from people who survived this episode. This is a picture from midday in London. People who abandoned their cars because they couldn't see where they were driving. The visibility was so poor during this one episode. And there were large health effects from the air pollution. Now, surprisingly, it was not the medical community who first noticed these health effects, but the people who are involved in businesses around people who have died. It was the undertakers who were running out of coffins, and florists who were running out of flowers for funerals. That's how much higher the death rates were during this episode. Let's look at some data from this. So here I'm showing, over the course of this episode, this is the bad air pollution episode here in gray, the air pollution that was measured at the time, which went up and then came back down, and the mortality rates, which you can see went up, and then they came back down, but not quite to the pre-episode level. It actually took a few weeks before they came back down to that level. So you do not need sophisticated statistics to pull out the signal from the noise here. Several-fold increase in air pollution and in death rates. There were 5,000 to 10,000 people who died as a result of this episode. Because of this event and other similar events in Europe and in North America, the thinking that followed from this was, well, when air pollution levels get to be too high, there are health effects, and so we need to figure out what are the safe levels of air pollution, and then keep the concentrations below those safe levels. And that thinking carried forward for several decades after this event, until the publication of this journal article in the New England Journal of Medicine by Doug Dockery and colleagues in 1993. And whereas the previous event was a short-term event looking at short-term health effects, this was a chronic study looking at long-term health effects from long-term exposures to air pollution. So here's 2 figures from their publication. Let me step through these. The figure on the left, this is years of follow-up, so you're looking more than a decade of exposures. This is called the Harvard 6 Cities Study. So they tracked thousands of people in these 6 cities. On the y-axis here is probability of survival, and there's one line for each city. So what you see is at year 0, the start of the study, the probability of survival is 100%, because the precondition for enrollment in the study is you had to be alive to get into the study. And then the study moves forward, and this is thousands of people, and so people start dying. And what they notice is that in the dirtier cities, death rates were higher than in the cleaner cities, even after accounting for other explanatory variables like cigarette smoking, education, affluence, and so on. And in fact, when they looked at the death rate normalized to the cleanest city, so that's what you see here on the y-axis is the death rate ratio. Here's the 6 cities that they studied, versus the air pollution concentrations. They're looking at fine particles, or PM 2.5, meaning particles smaller than 2.5 microns in diameter. These 6 data points lined up on a nice, clean, clear, straight line. A surprisingly clear and strong relationship here. So I want you to take away two things from this plot. One is there's not a safe concentration we can identify from these data points. When you look in this range of concentrations, what you see is that at dirtier concentrations, risks are higher, and at cleaner concentrations, risks are lower. But we can't pull out a safe level above which there's no added risk. And the second thing to notice is the magnitude of these values on the y-axis, that in the dirtier cities, you see mortality rates are elevated by 10, 20, 30% higher as a result of the air pollution. So I wanted to step through a simple back-of-the-envelope calculation for what this would mean in our city. What does this look like? In the Twin Cities, the air pollution levels are about 9 micrograms per meter cubed. So this is a mass per volume concentration. And what would happen if we were to make improvements in the concentrations in an already clean city? I'm going to use a different long-term health effects study. This is by Arden Pope and colleagues in the Journal of the American Medical Association. And I have here one sentence from their abstract, which I'll just read out. They found that each 10 micrograms per meter cubed elevation in fine particle air pollution, this is still PM2.5, was associated with approximately 4%, 6%, and 8% increased risk of all-cause, cardiopulmonary, and lung cancer mortality, respectively. Okay, so let me just start with that first number, the 4% increased risk of all-cause mortality, meaning total mortality rates. So I need to look up one piece of information for Minnesota, which is what are the all-cause mortality rates, and that's available online. There are 766 deaths per 100,000 people per year. Okay, that's one piece of information I needed. And then I have an example calculation. That thought would be helpful to step through, and this is my example. What if we take the Twin Cities, which is a population of 3 million, and if we were to reduce PM2.5 by 2 micrograms per meter cubed? And that's a reduction of about 20%. So if I want to look at what would be the health benefits of this improvement, all the numbers I need for this calculation are up on the board already. So stay with me if you wish to. You don't have to, but here, let's go. So we're going to reduce by 2 micrograms per meter cubed instead of 10. So instead of a 4% improvement, we'd see 2/10 of that, which is 0.8%. So you get death rates would decline by 0.8%. And here's our death rate. So let's see, 1% of this number is 7. 0.8% of this number is 6. 6 fewer deaths per year per 100,000 people. And then the last step to scale up is per 100,000 people. To get to 3 million, I have to multiply by 30. So 6 times 30 is 180. 180 fewer deaths per year are expected. This is a simple calculation as a result of this improvement in air pollution. That's a large number. I'm going to argue that's a relatively large number. Now, we don't know who those people are. If we did, air pollution regulation would look very different. Instead, we have already existing deaths, right? You're never going to find air pollution listed as the cause of death on a death certificate. But instead, we have deaths from lung cancer and heart disease and lung disease and many other factors which are elevated slightly as a result of the air pollution. Or in this example, if we're improving the air pollution, those death rates would go down slightly. One way to look at the magnitude of these impacts is to step into the world of economics and try to put economic values on these health impacts, which of course is a dicey business. What's the value of a life and so on. But let me just do that calculation to see what it looks like. This is called a statistical life that we'd be saving here. And what value do you use for a statistical life? Well, there's a range of values. But a typical number that EPA uses is $9 million per statistical life. And so if you do that calculation and multiply $9 million times 180 deaths, you get a number that's north of $1 billion per year in economic benefits. So that suggests that we in the Twin Cities should be willing to spend a lot of money, hundreds of millions of dollars or more per year, if those investments would lead to this level of air pollution improvement. That's an example locally. Let me turn to what this looks like globally and where air pollution fits into the bigger picture in terms of other risk factors. So to do that, I'm turning to something called the global burden of disease, which is a major collaboration globally by the World Health Organization and Harvard School of Public Health and others to look at the risk factors for death and disease. These are in rank order, and each bar is colored for high income in the darker color and middle and low income countries in the lighter color. And I want to call your attention to 2 of the risk factors that are listed here. I'll start with this one here, ambient particulate matter pollution. You can see this is on a top 15 list. There's some dark blue here for high-income countries, so this is an issue locally, as well as globally in this lighter color. And in fact, if you just look at the high-income countries, air pollution is the largest environmental health risk factor. And in fact, not only is it the largest factor, it's also responsible for a majority of the environmental risks that we face come from air pollution. And then this other issue up here, household or indoor air pollution. There's not a dark part of this bar. This is not an issue locally. It is an issue globally, primarily in low-income countries. So this is cooking and heating from solid fuel, from wood, cow dung, agricultural waste, coal, whatever fuels are available that are free or inexpensive. And in the case of cooking, that would be exposing the women, realistically, who are doing the cooking in low-income communities, and any small kids who happen to be nearby them, leading to very high concentrations. Imagine you have a barbecue and you bring it into your bedroom. That's the very high concentrations that people are exposed to day in and day out just for cooking and heating. And so perhaps not surprising that the health effects from those very high concentrations over long term are quite high. Now, if we want to make improvements on these health effects, we typically would start thinking about a causal chain between the emission source and the exposure to the emissions from that source, and then the health effects from those exposures. My area of focus is here in the middle on exposures. And we use various methods to understand these exposures. So at one extreme, we use satellite measurements to try to look at how air pollution varies in space. And I'll show some examples of that. At the other extreme, we can do direct measurement, give people a backpack with air pollution equipment. They go about their day. At the end of the day, you come in and analyze a filter, or you have a real-time instrument that you can download the data from to a computer and look at what we would measure in the air that they're breathing. And then there's models. There's all kinds of models. They come in all different shapes and sizes. There's mechanistic models and statistical models. And I'll give some examples of air pollution models and how we use them. And the purpose of understanding the exposure here in the middle is that we want to go upstream in this causal chain to look at what are the sources that lead to those exposures and what would happen if those emissions were to go up or down, how would that change the exposures. And then downstream, looking at the health effects. If there were changes in exposures, what would be the health impacts of those changes in exposures? So with that, let me move on to 3 research projects that I'm working on that illustrate examples of those 3 different approaches that I just mentioned: satellites, direct measurement, and models. And the 3 projects I'll talk about, one is urban design, that is how the size and shape of a city can impact the air pollution levels in that city. The second is household pollution or indoor air pollution in rural India, and an intervention that we were involved in that tries to reduce emissions and improve exposures in rural contexts. And the third topic is biofuels, and what are the air pollution and health impacts of biofuels versus the fossil fuels that they might displace if we were to use more biofuels. An important theme underlying all these investigations is environmental justice. Who's more exposed to air pollution? Who's less exposed to air pollution? How does that correlate with demographics, like income and race? Are the burdens, the health effects felt equally amongst the population? So that question runs throughout many different investigations, and I'll turn to it explicitly at the end after going through these three topics. So with that, let me move to the first topic, which is urban form and air quality. And again, the question is, how does the size and shape of a city relate to its air pollution? And to look at this, we have a database of 90 cities globally, which are shown up here. I'm also showing the satellite-based estimates of ground level air pollution. And then this is showing a zoom in on one city in our database, which is the Twin Cities. And so you see, based on satellite imagery, where the land is built up for urban development versus not. You see the estimates from the satellite of air pollution. This is NO2 air pollution. The grid cells here are about 10 kilometers by 10 kilometers. So it's not as precise as we would like spatially, but it's precise enough to pick up this rural to urban gradient. And then this third map is just overlaying these first 2 maps to look at what are the air pollution concentrations as you move across the Twin Cities. And so we do this kind of investigation for each of the cities in our database. We look at the urban form, and we also know information about population and population density and income levels and so on. And then we look at different aspects of urban form, the size and shape of the city. And I'm showing 2 examples up here. On the left is compactness, and compactness is a measure of circularity. So the upper two cities, these are two cities I grabbed from the database, the upper two cities are more compact. They're more circle-like. And the lower cities are less compact. They're more shaped like a cigar. And the question is, does that aspect of urban form matter for air pollution? And in fact, in our work, we found this is not a statistically significant predictor of air pollution, compactness. And the next measure I'm showing here is contiguity. And so this is a question of how contiguous is the built-up area? So what percentage of the built-up area is contiguous with or in contact with the urban core? And you see on the right, these cities are more contiguous. So a much larger fraction of the built-up area is in touch with the urban core. On the left, you have cities that have less contiguous growth. That is, it's patchier. There's more leapfrog growth. And this is a metric that we see is correlated with air pollution concentrations, even after accounting for other explanatory variables, where the more contiguous cities, on average, tend to have lower air pollution than the less contiguous cities. So the point of doing this research is to start to pose the question, can we use urban form as a tool for air quality management? This is ongoing research. We've done an investigation internationally and an investigation in the US specifically. The work we're moving towards is, so far we've done cross-sectional analysis, meaning a snapshot in time. And so we're moving towards panel data, meaning how do things change over time in many cities. That's one area. A second area is to start to look at environmental justice questions of who's more exposed and who's less exposed and how does that relate to urban form. And the third issue is spatial precision. So I showed you the map of the satellite data with the 10 kilometers by 10 kilometers grid cell, which is enough to get urban to rural gradients, but it's not spatially precise enough to do a good job with environmental justice questions. And the same thing is true if you look at the EPA's monitoring data. There's not enough monitors to pick up spatial variability with enough precision to do a good job with environmental justice questions. So we've been working on a tool that supplies that additional spatial precision needed to look at environmental justice and other types of questions. And what I'm showing here are predictions from this model. This, again, is NO2. The predictions are based on EPA observations and the satellite data and land uses. And we use the land uses because we know those with really high spatial precision. Where are the roads, where the population density is higher or lower, industrial areas, and so on. So this map on the left is for the whole US, and we have predictions for each of the census blocks. A census block is the smallest area that the census works on. And I'm showing here a zoom in for the Twin Cities, and you can show there's much better spatial precision, much less than a kilometer scale spatial precision to these predictions. And then here's this line that I just drew arbitrarily across the Twin Cities, and here I'm looking up the modeled NO2 concentration as you move across the Twin Cities. And I did this just to show you can see this urban to rural gradient. It's picked up here in the predictions. And as well, all these little zigs and zags up and down are as this line crosses roads or parks or various land uses where you'd expect the concentration to go up or down. This model is able to incorporate those aspects of spatial variability. So we're using this in the urban form analysis, and then we're using this in environmental justice questions, which I'll come to at the end of my talk. With that, let me turn to the second topic, which is indoor air pollution in India. So I gave some numbers previously that were global. Here I have a number for India specifically. This is an estimate that about 500,000 people per year die because of biomass use indoors in rural areas. That's a shockingly large number. It's about 5% of the national burden of disease is attributable to this action that you see up here in the picture. People cooking day in and day out. We wanted to see if we could do something about this. Can we make an improvement on this? And so in our investigation, we're looking at a newer stove to see if that newer stove leads to improved emissions, that is emission reductions, and improved health effects. So here's a picture of the newer stove. In the lab, the stove looks great. It has a 3-fold increase in thermal efficiency, meaning how much energy gets into the pot per kilogram of wood. So it looks really good in the lab. You use less wood per meal and so on. Here's a picture of a traditional stove, what you might call a 3-stone fire. There's 3 spots where the pot is in contact with the stove. There's a nice wide opening here that you can put the wood in. This is the same fire that people have been using for thousands of years. And here you see the improved stove. This one is called a chulika. It's a rocket stove is the type of stove. It's shaped like a flower pot. There's an opening in the side where the wood goes in. There's a grate that the wood sits on so air can get in underneath the wood. That helps with the thermal efficiency. There's a heat shield here that puts more of the heat into the pot. And then in the hearth, what they've done is they've removed the old stove, which may have looked something like this, put in this U-shaped space that the stove can sit in. And there's room for 2 burners here. And over here, you see the old stove, which would be removed and destroyed in this case. So our approach was based on 2 things. One is field work. The stove works great in the laboratory. Let's see what it looks like in the field. We partnered with an NGO, Samuha. They're a great group. They're based in Bangalore. And this intervention happened in northern Karnataka in the south of India. They were doing this intervention anyway. They were making the stove and giving it at highly subsidized rates or selling it to communities. This is a CDM-funded project, so if you're familiar with the clean development mechanism of the Kyoto Protocol, it's a funding mechanism, and this NGO was granted approval. In fact, they were the first cook stove change-out that received CDM approval, so that's part of why we studied them. And we worked in one village of about 200 households, and we did a randomized control trial. So in this community, we measured air pollution and health levels in all of the households. And then randomly, half of the households were allocated the new stove. We gave people a few months to get used to the stove, and we came back and we remeasured air pollution and health in the intervention and non-intervention households. So that's our approach. Let me say a little bit more about this picture. So this upper box here is measuring at kind of breathing height. We have a bunch of equipment here to make measurements of things like black carbon and PM and some gases. And then this box down here, there's an inlet that goes up and into the chimney. And we do that because then we can directly sample the exhaust from the fire, and we can make estimates of emissions factors, not just concentrations, but emissions factors. You'll notice that this inlet valve has a mesh over the inlet, and that's to prevent insects from coming in and going down this pipe and into our air pollution equipment. We learned the need for that one the hard way. And that points out this other issue, which is it's really difficult to do robust air pollution measurements in this kind of context. If things go wrong, there's no hardware store that we can run to. The infrastructure is challenging to work with. The electricity is not reliable. The roads are bumpy. Concentrations are really high, and it's hot conditions. And that's challenging for the equipment, and it's challenging for the researchers who are in this environment day in and day out, coming here before sunrise to make measurements because people are cooking before sunrise so they can be out in the field when the sun comes up and so on. So all of the data that we get from this kind of field work is hard fought and hard won to make these measurements. We found a whole bunch of issues we didn't explain. We didn't expect a whole bunch of issues. So here's a picture of one person's kitchen, and what's wrong with this picture? What's wrong with this picture? If you're unsure, you should ask, is this an intervention or a non-intervention household? You've got both kinds of stoves here. So this is an example of an intervention household that opted to go back and get the traditional stove also. Why would they do that? You know, we're working with a great NGO. There's a significant amount of trust between the community and the NGO. They're in this village on a near daily basis. And they're saying, please follow protocol. And this is a household that said, no, thank you. Well, the newer stove is more efficient, and it burns hotter. And that's good for cooking some foods and not good for cooking other foods. So when faced with the option of having only a hotter burning stove or getting a hotter and less hot burner, they opted to have both. It's more convenient. It's no different than what you would see in a household here. Right? When I got a microwave oven, I didn't throw away my range top. And I got a toaster oven and a coffee maker. You know, when I buy a waffle iron someday, I'm not going to throw away all those other pieces of equipment. They're niche devices. They give me niche cooking opportunities. They partially substitute for and partially add to my cooking needs and my cooking energy consumption. So the same thing happens here. As you get new cooking devices, they kind of partially add and partially substitute for. And so this is called stove adding, is what we see here, instead of stove replacement. So we went in thinking we had two kinds of households, the intervention and the non-intervention, and it turns out that we had three kinds of households. The intervention who followed protocol, about a third of the intervention households didn't follow the protocol, and then the controls, the non-intervention households. If we only do the comparison looking at the controls versus the interventions that followed the protocol, then things look good. They don't look great. There's a statistically significant improvement in the intervention households that followed protocol relative to the controls. It's not a large improvement. It's not large enough that I get very excited about it, but it is a statistically significant improvement. If you look at the intervention households that didn't follow protocol, things got worse. They have more fires burning here, so things definitely got worse. That we see in the data. So you go in with good intentions with a stove that works well. If you fold together both kinds of intervention households, you actually do not see an improvement in air pollution or in health. So let's see, we're looking in one village. This is one study. My hope is that there are other studies out there happening, and of course there are. Even here in Institute of the Environment, Jill Baumgartner is doing studies in China. There are other people doing similar kinds of controlled interventions. From our study, we don't see this as a strong enough intervention to call it a solution, especially when you account for this case that a third of the households didn't follow the intervention protocol. We do know that the field is not the lab. And so it's really important in this context to get out in the field, despite the enormous challenges and complexity logistically of making measurements there, of seeing what happens in the field. And we experienced some issues here. If you went to another village, you might see a different set of issues that arose there. So with that, let me turn to the last topic, which is biofuels. Now, of course, there are a long list of reasons why people are interested in alternatives to petroleum. And my work is on energy and air pollution. And so I'm going to focus on the air pollution health effects and climate emissions shifts that we'd expect from biofuels relative to the fossil fuels that they might displace. And we look at several fuel alternatives. And so I'm listing them up here. One are hybrid electric vehicles. And the advantage of these vehicles is that they're more fuel efficient. This would be like a Toyota Prius, for example. We look at alternative fuels like diesel or compressed natural gas, CNG. For biofuels, we're looking at ethanol from corn grain or from corn stover. And then for electric vehicles, it depends on where the electricity comes from. Grid average, coal, natural gas, corn stover, which you can co-fire with coal to displace some of the coal use. And then renewables, so wind, wave, or solar power, WWS. We're looking not only at the emissions from the tailpipe, but also from the whole life cycle. This is a collaboration with Jason Hill and looking at what are the processes that lead to these fuels being available. So in the case of petroleum, you need to mine the petroleum out of the ground, bring it to the refinery, and then bring it to market. For biofuel, you have to grow the crop, which involves fertilizers. You have to make the fertilizer and then bring those crops to a refinery and bring them to market and so on. So we're looking at the whole life cycle. And then, so not only what the emissions are, but where those emissions come from. I have a movie here. So this is our air dispersion modeling. And what we do is we start with a base case of our emissions. That's up here. We're predicting for every hour over the course of the year. So you see the hours ticking by right here. And then we have all of our different possible fuels. And so what we do is we say, what would happen if vehicle miles traveled increased by 10%? And in each scenario, we allow that 10% increase to come from different fuels. We see what would be the changes in emissions, where those emissions would happen, when those emissions would happen, and make predictions about the changes in air pollution. Here I'm showing PM 2.5 relative to the base case. So this is the base case. Everything else here is relative to this base case. And you can see that for the different energy sources, there would be different locations that the pollution would come from. So we do this for a whole year, look at the changes in PM 2.5, and then step forward and make predictions about the health effects, and as I'll show in the next slide, estimates of the monetized value of those health effects from these changes in air pollution, from a hypothetical shift to biofuels or other fuels. So here I'm fast forwarding to the results, which combine air pollution and climate change impacts. Of course, there's a number of assumptions that I'm skipping over that I'd be happy to talk about in the Q&A afterwards. I'm using the $9 million as a value of a statistical life here. I'm using for the price of carbon what was on the European market yesterday. We put these numbers together. That's a relatively low number. So if I use a different price for the value of carbon, I'd see larger monetized impacts from the climate change. But actually, that ends up not changing things very much. There's only one case down here, electric vehicles from corn stover, where it shifts the balance, but only slightly. So this is all normalized to gasoline. So a value of 0 would be the same as gasoline. A negative value would mean lower environmental impacts than gasoline. You see there are several examples of negatives. And a positive value in this case means higher than or worse impacts than gasoline. And in cases where you have a plus and a minus, these triangles show you the net impact. So in this case, corn grain ethanol, you have a small climate benefit and a large air pollution disbenefit, and the net impact is a net disbenefit relative to gasoline. The largest negative here is for electric vehicles from coal. Perhaps not surprisingly, very large air pollution health impacts of coal. The largest benefit is electric vehicles from wind, wave, and solar. So this is renewable-based electricity that gives us the largest benefit. And again, there are several examples over here that are on the left side of this line that are environmental benefits relative to gasoline. The second largest bar is electric vehicles powered by natural gas. And the third largest bar is gasoline hybrid. So this is like the Toyota Prius. There's many people who have come to the same conclusion that increasing fuel economy is a really good way to go. And that's what we see here as well. This is one of the largest bars up here. So we're hopeful that this kind of analysis is useful in the policy arena in deciding which kinds of fuels should we turn to help address air pollution impacts, and which ones should we not turn to? Which ones are better for society than the fossil fuels that they would replace? And with that, let me turn to the third topic, which is environmental justice. And I have 3 slides here. The first is showing some modeling work we did for Southern California. We're looking at exposures for 3 pollutants: ozone, diesel particles, and benzene, these 3 different bars, for whites, Hispanics, African Americans, and Asians and Pacific Islanders. And what you can see is that there's differences by pollutant and by subpopulation. So for diesel particles and benzene, whites have lower exposures, and non-whites have higher exposures. And for ozone, the reverse pattern holds. Whites have higher exposures, and non-whites have lower exposures. What's going on here?
Whites are more likely to live in the suburbs, the surrounding areas.
Yeah,
Ozone forms.
Exactly. Yeah, that's exactly right. There's different spatial patterns to these air pollutants. So diesel and benzene are directly emitted pollutants. Their higher concentrations are downtown and near freeways. And those are regions that, on average, have fewer whites and more non-whites. Whereas ozone is not directly emitted. It's formed in the atmosphere from chemical reactions, which take a little time to happen. And so the high concentrations are not downtown and not near freeways. Instead, they're in the suburbs, in the Los Angeles case, in the eastern suburbs, which are more likely to have whites on average and which have fewer non-whites. And so you get higher exposures to ozone for whites and lower exposures for non-whites. This is for one particular urban area in Southern California. Let me turn then to a national analysis we did. And this is, I put this icon up here to remind you of the land use regression model that I described previously with really good spatial precision. And we're looking here at household income and race, white or non-white, for rural areas, and then small, medium, and large urban areas. So what we see is that, on average, higher income, this is based on census block groups. So on average, areas that are higher income have lower air pollution in urban areas. In rural areas, it doesn't actually matter all that much. And in all 3 cases, whites have lower exposures than non-whites. In the case of large urban areas, race ends up being a more important predictor statistically than income, although they're both important. And in medium and small urban areas, they end up being about equally important, race and income. So this provides a national context as opposed to a local context, a national context for environmental justice, for understanding how things vary nationwide. We can look at how things change over time. And since we have this excellent spatial precision for throughout the US, we can start to look at which areas have larger or smaller environmental justice concerns. That is, how far are their deviations from equality? And in fact, we have two different metrics, environmental justice and environmental equality. And those are two terms that are often used synonymously, and they mean slightly different things. Environmental equality is indicating how close are we to everyone being equal. That doesn't get into who's more exposed and who's less exposed. So what I'm showing up here are those two different measures. This is an equality metric. This thing, the Atkinson index, or if you're familiar with this literature, you might use the Gini coefficient. They're metrics that look at how far are we from perfect equality. And we're calculating these metrics by region, state, county, and urban area. And so this starts to look at which parts of the US have greater deviations from complete equality in exposures. Again, this column doesn't get at who's breathing more or less air pollution, just what's the disparity relative to perfect equality. This second column gets at that issue of who's breathing the air pollution. So here what we look at is the difference between higher income whites and lower income non-whites. What's that difference in exposure concentration? Again, by region, state, county, and urban area. And there's some degree of overlap and some difference between these two metrics. They're just measuring fundamentally different aspects of the correlation between how pollution varies in space and where people live. So different aspects, environmental justice versus environmental equality. So we'd use this kind of analysis to say, okay, where should we focus? If we care about environmental equality or environmental justice, where are the regions that we should focus in on where we see the largest disparities? So I will wrap up there and just summarize what I talked about so far. My research is in exposure to air pollution. I talked about three methods, using satellites, using direct measurement, and modeling. I had three research questions that matched with those methods. Urban design and how the size and shape of a city correlates with air pollution. Indoor air pollution in rural India, and we studied one intervention to see if it could make an improvement on those health effects. And then biofuels and the air pollution and health impacts relative to the fossil fuels that they might displace. So with that, thank you for your attention, and I'm happy to take questions.